Now let's talk about a uniformly charged ring. So what about if you have a ring and you want to find the force exerted by that ring of charge on a point in space? Okay, what happens? So a ring of charge, how will that affect it? So let's suppose that we have a ring and that has a positive charge on it. Why positive? Then I don't have to worry about negative signs all over the place, right? And I want to find, at this point, a test charge Q naught above it, about on its center, around its central line. I could only draw a straight line, right? Sort of in the center, so that will give you an idea. Now what happens in this case? So it's still, in this case, what we're going to be doing is we are going to be using R phi z instead of xyz. Okay? So what we're going to do is, again, we are going to divide these into small volume elements dq. And each dq, if this is r, which is the radius, and this is theta, so each dq is going to be represented by r and theta. Okay? The linear charge density, and this dq, this little section, dq, is going to exert a force on this test charge that's placed here. So the linear charge density is going to be Q over 2 pi r, because we are using cylindrical coordinates, right? And what are we looking for? We are looking for the force exerted by this ring of charge at a test charged Q placed at a distance, say, z. Okay? So if this is placed at a distance z, I can call this r, and I will call this a little r, that is the displacement away. Okay? Then this dq will actually be equals to r d theta. Okay? Times lambda. Okay? And cosine theta will be z over r. Now, similar to what we did last time, we are going to find df. That df will be equals to ke q naught dq over r squared, right? dq is r d theta lambda, and r squared, which is this r squared, is actually equals to r squared plus z squared. Okay? Where this is the r and this is the z and this is the small r. Okay, so this is going to be my df. Now, which df are we talking about? The same way as we tried to calculate last time, we're going to figure out what's going on. First off, so I'm going to use the red marker for this. So first off, we are going to try to calculate what Fr is, the force due to R. Well, what happens to Fr? The segment here and the segment here on opposite sides will have opposite effect on dq. So from symmetric arguments, this is equals to 0. Okay, they cancel each other out. Similarly, the component Fy will also be 0. So the only one that's going to be left is Fz. So the only one that contributes to the force acting on this test charge is going to be the force along the z-axis. So we will know that F equals that. Okay? That means this is going to be df cosine theta. Okay? Once we have that, then we can plug in the values and be able to solve it. Okay? So this one is df. I can easily put that in. It's going to be ke q naught r d theta lambda over r squared plus z squared integration. And cosine theta, as I know, is z over r. Okay? What is the integration over? The integration is only over d theta, right? So everything else comes out as a constant. R lambda z divided by r squared plus z squared r. And the integration is going to be over d theta. What is d theta? D theta is this. So it goes from 0 to 2 pi. Okay? So what do I get? I get f, which is equals to, again, because we're integrating it, this becomes f, right? All the other components go to 0. Ke q naught r lambda z divided by r squared plus z squared r 2 pi. Okay? Now what was lambda? Lambda was equals to this, and ke remains that q naught r q over 2 pi r z 2 pi divided by r squared plus z squared. Okay? What do I get? 2 pi's go away. And this is going to be, since this is now the total, it's going to be over capital R, not little r. So this is going to be capital R. So r's will go away. And we will get ke q naught q divided by z divided by z squared plus r squared 3/2. Oh, sorry. The reason why I'm missing an r is because this 3/2 includes this r. If you look at it carefully, r actually equals z squared plus r squared, right? So this r actually equals z squared plus r squared square root. So I can plug that in here. Instead of this r, I can plug here r squared plus z squared 1/2, right? 1/2 plus 1 equals 3/2. So my total force comes out to be this one for a ring of charge. Okay? Now, in the limiting case, where z goes to infinity, that means z is much, much greater than r. That means r can almost go to 0. What you are going to find in this limiting case, f will be 1 over 4 pi epsilon naught, which is ke, q naught q over z cubed z. This gets canceled, it becomes squared, and f will become equals to 1 over 4 pi epsilon naught q naught over z squared. This is, again, the same thing as it was if this goes really, really far down and the point is still there. It's almost like an interaction between 2 point charges, and that's what we see there. Another really good example is the example that's given in the book that's called the disk of charge. In this case, the difference between me solving that this way or you solving it is the fact that it is, instead of now talking about a linear charge density, you are going to now talk about surface charge density. The steps that you follow to come up with the answer are exactly the same. The only difference is instead of linear charge density, now you're going to be talking about surface charge density. I would highly recommend that you go ahead and go to the book and actually see how it's solved.